Alright, so it's important to be able to draw situations where shapes are inscribed and circumscribed. So we talked about how inscribed kind of sounds like inside. So when you see inscribed, you're thinking inside. But it's not just inside, because that is not an inscribed triangle, because it is not, the vertices of the triangle are not on the circle. So be careful when you're inscribing and circumscribing. It's kind of like you're making that shape as big as you can possibly make it without overlapping, without going outside the other shape. Okay? So let's take a look at what these two situations look like. There's an equilateral triangle inscribed in a circle. Notice how the triangle's vertices are on the circle. The circle has a radius of 10. So there's the radius of the circle. And you would want to draw the radius in a part where the radius is part of the triangle and part of the circle. So you would not want to draw, if you were drawing it, that radius of 10. That one would not help you at all. So don't draw the radius that goes outside of the triangle. Draw the one where you can look at the radius in reference to both of the shapes. Okay? So not that one right there. The next situation said to draw a square circumscribed about a circle. So when you see circumscribed about, you think outside, the opposite of inside. You want that circle to be as big as it can possibly be inside that square without leaving the square. So the circle is going to touch the square 4 times. 1, 2, 3, 4. And that's where we drew the radius. The radius that we would not draw would be like that radius of 10. That one would not help us at all because it doesn't touch the square, the edge of the square. Alright, so that's inscribed and circumscribed. Let's go back to the vocab that we started yesterday but we didn't get to finish. When we are learning our new formula today, which I haven't revealed yet, this new formula, it only works on regular polygons. So you can't use it on a polygon that's not regular. So what does it mean for a polygon to be regular? You probably remember this from last semester. A regular polygon is a polygon where all sides are congruent and all angles are congruent. So it's perfectly symmetrical. All angles, all sides, the exact same length or the exact same measure. Okay? The next word, that word is called an apothem. That's a new word for us. Some people say apothem, some people say apothem, but the correct pronunciation is apothem. Yeah, it sounds like a possum, doesn't it? The animal that sleeps upside down. I said apothem for most of my life, so if you say apothem, it won't really bother me. But correct way to say it is apothem. So this is a picture of an apothem. What do you think it is? Thank you for plugging your cameras in. It is a segment that goes from, what do you think? From the center of a polygon to, yeah, it will be a midpoint, but it goes from a center to a side, from a center to a side. And it's the perpendicular distance. So it's kind of like an altitude. An apothem is kind of like an altitude, except it doesn't go all the way up. Very good. Perpendicular distance from the center of the polygon to a side. So write that down so you know what an apothem is. And then the last word we have is radius. Take a look at the apothem and the radius. The apothem and the radius. Do you see how they're different? An apothem goes from a center to a side. A radius goes from the center to a vertex. So one of them goes from the center to a side, and the other one goes from a center to a vertex. Okay? So apothem versus radius. You need to keep track of the difference between those two. Let's keep going. So here I have a nice, beautiful, regular pentagon. Okay, so what I'm going to do first is I'm going to show you what happens when the pentagon is inscribed in the circle. Okay. When the pentagon is inscribed in the circle, the radius of the circle is the radius of the pentagon. The radius of the circle is the radius of the pentagon. Now, if I circumscribe the pentagon, then the radius of that circle, the coral colored one, the radius of the circle is the apothem of the pentagon. Okay? And the radius and the apothem in half of the side, together they make a nice right triangle. So what kind of tools do we use when we're working with right triangles? What kind of tools do we use? Yep, we use trig sometimes. We use Pythagorean theorem. And sometimes we use special right triangles, right? 30, 60, 90, 45, 45, 90. Okay? So that is important. Let's dive straight into the formula. I'm not going to derive it for you because we're trying to kind of squeeze a lot in one day. We're just going to dive right into the formula. Here's the formula for the area of a regular polygon. So write that down, please. You'll see it on your formula chart as 1/2 AP. So we need to know what these things stand for. The A stands for apothem, the apothem of the polygon, and the P stands for perimeter. And of course, the perimeter, you just take the side length and multiply it by how many sides it has. Since it's a regular polygon, you don't have to add them all up. They're all the same length. So you can multiply. So if the side length is 3, and it's an octagon, 3 times 8. If the side length is 3 and it's a dodecagon, 3 times 12. That'll get you their perimeter. So capital P stands for perimeter and lowercase a stands for apothem. Okay, let's try one. I'll give you a second to write that down. Find the area of a regular hexagon inscribed in a circle with a radius of 4√3. Whew! Yes, Thielemann, it only works for regular polygons. If the polygon is not regular, like that, you would have to divide it up into triangles. You have really no other way, or a trapezoid and a triangle or whatever. You have no other way to find it other than to divide it up into other shapes. It only works for regular polygons. All right, so the first thing we need to do is we need to make sure we put this side length, we need to put it in the right spot. It's inscribed in a circle with a radius of 4√3. So the radius, not the apothem, the radius is 4√3. So let's make sure we put this in the right spot. And then, we've got a right triangle and we only know one of the sides. So we better hope that that's a 30, 60, 90 triangle. We're going to use that later, so hold on to that, okay? The good news is, well, yeah, we can kind of use it right now. This is a hexagon. And a hexagon is one of our special cases that we're about to talk about. In a hexagon, you're right, you can do n minus 2 times 180. Very good. And you can divide it by n. And you will find out in a hexagon, every angle of the hexagon is 120. Every angle. Now, since this is a regular hexagon, when I draw the radius, it's going to cut that angle in half. So when I take 120 and I cut it in half, I get 60. So there's our 30, 60, 90 triangle. So I'm going to go through this rather quickly. Across from 90 is 4√3. So across from 30 would be 2√3. And across from 60 would be 6. 2√3√3. 2 times 3. Hopefully y'all are okay with that. Did I go too fast or are we okay? I cut 4 root 3 in half, and then we did x root 3, 2 root 3 root 3. All right, we're ready for the area because now we have all the pieces of our puzzle. So what I would do first is I would find the perimeter off to the side, or you can find it while you're doing the area. It doesn't matter. One side length, the whole side is 4 root 3. That's one side. There are 6 sides, so the perimeter is 24 root 3. All right, my formula says apothem times perimeter divided by 2. Apothem times perimeter divided by 2. So now remember, we're not going to press root 3 in our calculator. We're not going to press it. We're going to do 6 times 24 divided by 2. And that gets us 72. We attach the root 3 at the end. You don't forget about him. And then we put units, centimeters squared. Okay? Moving on. I mentioned something. I said something about how that was a special case. Well, there's 3 special cases where you don't have to use trig. These are the 3 times that you do not have to use trig. The rest of the ones you're going to have to use trig, unless I give you 2 of the sides. So if you want to write these down, if you want to note, these are the 3 times when I get to use my shortcuts. These are our shortcuts. So equilateral triangle, 30, 60, 90. Square, 45, 45, 90. And hexagon, 60, 30, 90. So you do need to be aware of where the 30 and the 60 goes. It's really important. If you get those mixed up, you'll definitely get your answer wrong. Those are the only 3 times, EG. So pentagon, got to use trig. Heptagon, you got to use trig. Octagon, you got to use trig. Nonagon, you got to use trig. And we'll do one of those at the end. That'll be the last thing we do. Okay, let's try another one. Where is our second problem? There we go. Find the area of an equilateral triangle with radius 6 root 3. I'm going to let y'all work on that for a second. So make sure you put 6 root 3 in the right spot. It's the radius, not the apothem. So this is kind of starting to look like the last problem. Now make sure you put the 30 and the 60 in the right spot. How I remember this one is that if this is an equilateral triangle, the angles are 60. Well, when I cut 60 in half, boom, I get 30. So make sure that 30 goes in the smaller angle. Okay, ready? Let's just keep moving. It's the same as last problem. Across from 90 is 6 root 3. So across from 30, we're going to half it. And then across from 60, it's 3 root 3 root 3, which is really 3 times 3, which is 9. So I hope that you're okay with that. Now, a common mistake that students make is they think that the side is 9. So be careful, you've found half of the side, you have not found a side. You've found half of a side. People get rushed and they're like, oh, 9 times 3, boom, I got my perimeter. No, it's not 9 times 3. So be careful. So I like to go off to the side and find the perimeter. And then you can just go straight to your area formula after you've done that. Okay, welcome back from your fire drill. So, we've got apothem, there we go, there's the apothem, times perimeter, there we go, divided by 2. Remember, we're not putting root 3 in our calculator, so we're doing 3 times 54 divided by 2, and we get 81. We tack on our root 3, don't forget about him, and then meters squared. Not so bad. You know what you did wrong, Helaman? Oh yeah, you got to include the 3 in the divide by 2. Okay? Here's our last special case that we're going to practice. Special case. It's special because we do not have to use trig. Radius of 4. It's kind of weird that you're given the radius of the square. It's like, come on, just give me a side and I can find the area. All right. So we're given a radius of 4. We automatically know that that's 45, 45, 90 because it's a square. What are the sides, what are the legs of that triangle? Who can type it first? What are the legs of those triangles? Of that triangle? No? Oh, Quan got it. 2 root 2. Very good. Now, I don't know if you noticed, if y'all did the circuit, but there were some problems in the circuit where I gave you a rhombus, something like that. And even though it was a rhombus, it made more sense to do base times height. You didn't want to do diagonal 1 times diagonal 2 divided by 2 because the height was 10 and the base was 10 root 2. It was too easy. You should have done base times height. So even though it was a rhombus, you used the parallelograms formula. Now, the reason I brought that up is because even though that this is a square, even though you have an apothem and you have a perimeter, I would not use that. I would just use my area of a square formula. I would do side squared. So just because I gave you an apothem does not mean you have to use the regular polygon formula. I would use the square formula. There's one of the sides. It's 4 root 2, the whole side. Side squared. So I would go back to a regular old square formula. That's just what I would do personally. Are we okay with the fact that that's 32, or do I need to explain it? 16 times 2. Does the apothem make 2 similar triangles? I only see one triangle. No, they'd be congruent triangles. Triangle 1 would be congruent to triangle 2, not just similar, but congruent. Anyways, the answer is 32. Okay, here's another example. And this time you have to draw the picture yourself. So go ahead and draw that picture. So it helps some of my students sometimes when they see circumscribed about, to write the word outside. So we've got a square outside a circle. So a square outside a circle. Something like that. The circle is the one with a radius of 16. So the circle's radius is 16. Be careful. The circle's radius is the square's apothem. Do you see that? The circle's radius is the square's apothem. You have to be able to draw these things. Well, now it's easy. Now I've got a square. Find the area of the square. I'm sorry. Does yours look better than mine? Okay, the side of this square is 32. Find the area of a square. 32 squared. There's no reason to use apothem times perimeter divided by 2. To me, that's more work. 32 squared, 1,024 feet squared. Are we okay with that? It's just knowing how to draw it. Okay, last problem of today's lesson. Here's where we're finally going to use trig, because this is a pentagon. It's not a special one. It's not a triangle, square, or hexagon. Find the area of the regular polygon to the nearest tenth. We've got an apothem. That's great news. But we don't have a perimeter. So we're going to need to find the perimeter. And believe it or not, we're going to have to draw this right triangle, the radius, and that's going to help us find the perimeter. Now, to do trig, we've got to have a side and an angle. We've got a side. We don't have an angle. Let me give you 2 options to find your missing angle. One of the options is to do what Helium was talking about earlier. You can do n minus 2 times 180 divided by n. N, of course, stands for the number of sides. So n minus 2 times 180 divided by n. Very good, Minjung. Ha ha ha. 108. But be careful. That's each angle. Each angle is 108. So we need to divide it by 2. So that's 54. So if you like that way, you do that way. let me give you another option if that formula is intimidating to you. What I like to look at is I like to look right here. If I went full circle, I would travel 360 degrees, right? Now, if I drew that triangle and I filled up the whole pentagon, I would be drawing 2 triangles per side, right? Every side would get 2 triangles. So there's 5 sides. Each side would get 2 triangles. Okay, so I would draw 10 triangles. So it's really 360 cut into 10 even parts. So that angle is 36. So there's another way to go about it. You don't need both angles. You only need one of them. So you can decide which angle you would rather look for, 36 or 54. Okay? I do too, EAG. That's my favorite way. So I'm going to go ahead and use the 36. And I know that I'm looking for a side. So that's my X right there. So I'm going to say tan of 36 equals opposite over adjacent. So X is 6 times tan, 36. The next part is really important. I need you to get your calculator out and hold it. Hold your calculator with me. Hold it. Because I want to make sure we are not rounding as we go. We are not rounding as we go. So, everyone go to your calculator and type 6 tan 36. You should get 4.35. No, you can't see that very well. There we go. Okay. What did we just find? We just found half of a side. So I want everyone right now to do times 2. There's our whole side. 8.7 blah blah blah. Okay. Now we need to find perimeter. There's 5 sides. So do times 5. 43 point something. There's our perimeter. I'm not writing these down. I'm not rounding them. Okay? Perimeter times apothem, so times 6. And then divide by 2. I kept every number in my calculator until the very end. And you get 130.777. So if I'm rounding to the nearest tenth, that would be 130.8, and we don't have units. So I know, Helaman, I don't have them set up today. I can do it tomorrow, okay?